Welcome to the Stoichiometry of Precipitation reactions. So, the stoichiometric principles that were introduced previously in Chapter 9 apply to precipitation reactions. So, for example, let's calculate the mass of solid sodium chloride that must be added to 1.50 liters of a 0.1 molar silver nitrate solution to precipitate all of the silver ions as silver chloride. So let's first begin by writing the formula equation, the complete ionic equation, and the net ionic equation. So the formula equation is the sodium chloride in aqueous solution plus the silver nitrate in aqueous solution yield sodium nitrate in aqueous solution and silver chloride solid, because the silver chloride will precipitate out of solution. Now let's write the complete ionic equation. So the sodium chloride is ionic. It will dissociate in water in aqueous solution, so we have sodium ions and chloride ions. The silver nitrate is also ionic. That will also dissociate in aqueous solution, so we have silver ions and nitrate ions. And that reacts to give us the sodium nitrate is ionic and will dissociate in aqueous solution, so we have sodium ions and nitrate ions. The silver chloride is ionic, but it's not an aqueous solution. It's precipitated out as a solid, so we still have silver chloride solid here. So now you can see that we have some silver on the left side of the equation and some sodium ions on the left and sodium ions on the right. We have some nitrate ions on the left, some nitrate ions on the right. And that means that now we're left with chloride ions plus silver ions yield silver chloride. So that's what we write down here. Chloride plus silver ions yield silver chloride. So this is our net ionic equation, where we've removed the ions in the complete ionic equation that aren't doing anything. We've removed the spectator ions. So now let's find the number of moles of silver ions in solution. Well, we have a 1.50 liter solution. We know the concentration is 0.1 moles of silver in 1 liter of solution. That means that we have 0.150 moles of silver ions. And so now let's find the number of moles of chloride ions that's required to react with our silver ions. Well, we know that we have 0.150 moles of silver ions. We know that the mole-mole ratio of chloride to silver ions is 1:1. And that means that we need 0.150 moles of chloride ions. So now let's find the number of moles of sodium chloride that are required to produce the number of moles of chloride ions that we need. Well, we know that we need 0.150 moles of chloride ions. We know that the mole ratio of chloride ions in sodium chloride is 1:1. So 1 mole of sodium chloride per mole of chloride ions. So we know that we need 0.150 moles of sodium chloride. So now let's find the mass of sodium chloride that's required to obtain our number of moles that we need. So we know that we need 0.150 moles of sodium chloride. Multiplied by the molar mass, 58.44 grams of sodium chloride. And that means that we need 8.77 grams of sodium chloride. So note that we could have combined all of these calculations into a single calculation. We could convert from liters of solution to moles of silver, convert from moles of silver to moles of chloride ions, convert from moles of chloride ions to moles of sodium chloride, convert from moles of sodium chloride to grams of sodium chloride, and that, if you do the math, will end up giving us the same value, 8.77 grams of sodium chloride. So this is the way that I generally like to perform a calculation, unless I need to know one of these intermediate numbers, because if I plug this first calculation into my calculator and I write down the answer and I've rounded it, and then I plug in that rounded answer to my subsequent calculations. Now in this case, you're just multiplying by 1 for these two, so it's not going to matter, but you'll still have that rounded number times this 58.44. And if we have some other numbers in here, it may introduce additional rounding errors, because if you round after every single calculation, you're likely to introduce some significant rounding errors by the end of the calculation. Now you're still likely to be fairly close, but it's still better to try to do the calculation in as few calculation steps as possible. So if you plug it all into the calculator at once, you're more likely to get the right answer. So here we have some solubility rules. This is from the Zumdahl text, table 10.1. It's labeled simple rules for the solubility of salts in water. So rule 1 is most nitrate salts are soluble. Rule 2 says most salts containing the alkali metal ions, so lithium ion, sodium ion, potassium, cesium, and rubidium, and the ammonium ion, NH4+, are soluble. Rule 3 says most chloride, bromide, and iodide salts are soluble. Notable exceptions are salts containing the ions silver, lead 2, and mercury 1. So note here that this is Hg2+. This is a polyatomic ion. Most sulfate salts are soluble. This is rule 4. Notable exceptions are barium sulfate, lead sulfate. This is lead 2 sulfate, mercury 1 sulfate, and calcium sulfate. Rule 5 says most hydroxides are only slightly soluble. The important soluble hydroxides are sodium hydroxide and potassium hydroxide. The compounds barium hydroxide, strontium hydroxide, and calcium hydroxide are marginally soluble. Rule 6 says most sulfides, note that this is not sulfates, this is sulfides, where we just have a sulfur ion, S2-. Most sulfides, carbonate and chromate and phosphate salts are only slightly soluble, except those containing the cations in rule 2, the alkali metal ions. So, these are our rules for solubility. They don't cover everything, but they cover most things that you're likely to run into in general chemistry. And the rules at the top supersede the rules at the bottom. So, just like in rule 6, where it said most sulfides, carbonates, chromates, and phosphates are only slightly soluble, except those containing the cations in rule 2, that means that basically rule 2 supersedes rule 6. And so you read down from the top. So if you have some compound that contains a nitrate, you can stop. You don't need to read through the rest of the rules. You know that that compound is soluble. So the earlier reaction that we did, where we had sodium nitrate reacting, we had silver nitrate reacting with sodium chloride. The silver nitrate was soluble because of rule 1. But then when the silver reacted with the chloride, swapped the nitrate ion for a chloride ion, then we got down here to rule 3. Most chloride, bromide, and iodide salts are soluble, except salts containing silver. So in that case, silver chloride was not soluble, and that is why the silver chloride precipitated out of solution. So that was the stoichiometry of precipitation reactions.